All right, welcome back. So today we're going to continue with mathematical preliminaries. And then hopefully there'll be enough time to get into semi-definite programming. And I'll talk about the relevance of that in quantum information. I think next week we'll have to continue into with semi-definite programming. Oh yeah, I could have felt it. Okay, so I want to talk about some things that you might already know, but we'll just talk about anyway. So that thing is a limit, and that's because capacity is defined as a limit, right? So just some basic topics from analysis and the notion of a limit. So when we write, we have a sequence of numbers Sn, and we write this. It's a question of what does this mean precisely, right? So what is the meaning of this? So, taken a course on real analysis that you've seen it before. So it means this: for all epsilon strictly greater than 0, you can pick integer such that for all integers larger than that one, this inequality holds. Right? So you should really think of this as kind of like a game where someone else picks an epsilon as like a challenge to you, right? And then you're allowed to respond and pick an n large enough such that this inequality holds, right? And that will have a meaning with protocols that we consider for communication as well. Often we'll make an abbreviation. So rather than, and you'll see this if you read information theory papers, I think it's used in the book also. At least it's in my first book. So you'll see this abbreviated as for all epsilon greater than 0 and sufficiently large n. Sn, right? That it's less of a mouthful, and you just if you forget what it means, you just do this translation. But this is a very common abbreviation. And it really captures what this is saying, right? Like, sufficiently large n, well, it's just like as long as the n is larger than this n epsilon, and then for all those n larger than that epsilon, stay. Okay. So, to pull it up, then there's a notion of often we're maximizing or minimizing expressions. Related to that is taking a supremum or infimum. If you haven't taken a course in real analysis before, maybe you haven't seen the notion of supremum and infimum. So let's just talk about that briefly. So what is an infimum? Let's just consider a subset of the real line. Right? And we say that x is a lower bound for the set E if y is greater than x for all y in the set. Okay. So that's just the notion of a lower bound. What is the infimum? The infimum is the greatest lower bound. Okay, so if that's a new concept, then I think it's most easily demonstrated with an example, right? So an example would be let's take the set E to be It's called harmonic sequence, right? And so this is a legitimate set, right? It's a countably infinite set. And the question is, what is the theme of this set, right? Well, you can like draw it, right? So here's one, then the next one is the half, then the next one is third, and then et cetera, da, 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 right? And you know, everything over here to the left is a lower bound, right? And then there's a question of what is the greatest lower bound, right? And that's the infimum. So the greatest lower bound here is going to be 0, right? That's the greatest of all these lower bounds, right? Any of these are lower bounds, and then if I pick 0, it's still a lower bound. Why is it the greatest lower bound? If you take any number strictly larger than 0, then there's going to be an element of this set that's no longer greater than 0. No longer greater than the bound that you picked, or the number that you picked. Okay. So what this is the key example, I think, to think of when you think of infimum or supremum, because it shows you that the infimum need not be contained in the set, right? It's that's the kind of thing you'll encounter that like sometimes the minimum doesn't exist. For the most part in this class, the minimum will be the same as the infimum because the sets over which we'll optimize will be closed and bounded. What's going on here is that this is like an open set, right? Not quite that because it doesn't include all the real numbers. But this is also an example of a set for which the infimum is 0. Right? Okay, so it's worthwhile to mention that. The flip of this is the supremum. That's the supremum is the least upper bound of a set. So similar thing, X is an upper bound. If Y is less than X for all Y in the set. And then the supreme is the least upper bound. And then you can think about examples like we just talked about. Like this is a set, it's an open set, it doesn't include 1, but includes all numbers, all real numbers arbitrarily close to 1. The supreme of the set is 1. Also, in this set that includes 1, the supreme is also 1. So that's a case in which the supreme is the same as the maximum. Okay. We'll often use abbreviations like this. We'll take the infimum of a function over all elements in a set, and then it's worthwhile to just state that this means this. This is like a common shorthand that we'll use, but it just means you have some function that you evaluate for elements in a set, and then you take the greatest lower bound of the function over all elements in the set. Okay, you can do a similar thing for supremum, and then S could be some subset of the set of linear operators in a Hilbert space. Right? Like often we're going to be optimizing functions over density operators or over measurement operators. So this kind of thing will come into play. All right, related to this, there's notions of limit inferior and limit superior. If you have a limit of a sequence, it need not always exist, but the limit inferior and the limit superior always exist. So I want to talk about those for a little bit. Here's an example. So suppose this is your sequence. +1, -1, +1, -1. This goes on and on. The limit doesn't exist, right? But the limit superior and the limit inferior exist. In this case, the sequence is so simple that the limit superior is going to be 1. So it's like the limit superior is the least asymptotic upper bound. So we're going to define what we mean by that. Okay. The limit inferior is the greatest asymptotic lower bound. So a substitute for a limit that always exists so we abbreviate it as lim inf and lim sup. Okay. And then, if the lim inf is equal to the lim sup, then the limit exists, and it's equal to both of them. So let's define limit inferior. And when I write the definition of a asymptotic lower bound, it'll look like a one-sided definition of a limit, right? In the definition of a limit, we had an absolute value. So what this will be, it'll just be a one-sided version of the limit without the absolute value. Okay. So we said that S is an asymptotic lower bound for the sequence. That's not. Yeah. And then blah blah blah. For all epsilon 0, just n epsilon such that for all n greater than n epsilon, Sn is greater than S minus epsilon. So it's the limit. Right, so we can rewrite this condition here. And so that's another way to write it, right? And so that's how you can see it as like a one-sided version of the limit. It's always possible for any sequence to find these asymptotic lower bounds, right? Like you can take it to be negative infinity, and then you're good, right? But maybe you want to have a tighter lower bound, right? But the point here is that there might be all kinds of things that happen at the beginning of a sequence, right? But then for these limiting notions, we're only interested for what happens asymptotically, beyond some points, for all but finitely many, right? And so that's what this gives you. Okay, and then just like we defined infimum as the greatest lower bound, lim inf is the greatest asymptotic lower bound. Lim inf is the greatest asymptotic lower bound. If you go on, and we denote it by this. That's the notation of it. So we'll use these concepts when we define capacities or like achievable rates of communication. The reason we do that is that the capacity is a notion that should always exist. Right? It's an operational quantity that always exists. Depends on a sequence of protocols. And for many cases of interest, lim inf will just be equal to the limit. but still, like a priori, we want to define it in a way that the notion always exists in a meaningful way. Okay. And if you go on Wikipedia, there's like a lovely picture which shows like sequence doing this kind of thing. So it like oscillates a bit, but then it becomes steady, kind of like the +1, -1, right? And then the limit, I didn't do a good job. Maybe I could have made this like that. The limit is going to be, this point here, such that it's the greatest lower bound asymptotically. So really, beyond some point, the sequence will be always contained in this epsilon window. Okay. There's a similar thing. You flip everything around, and you get lim sup, limit superior. Okay. So if I flip it around, I think it's just these. I'll write the definition. Any questions about this? Yeah.
So, set greater than s minus epsilon.
Yeah. It's like you give a little wiggle room, right? The point is that it's for all epsilon. Like you imagine that someone else is picking the epsilon, right? It could be arbitrarily small, and then you're allowed to take n large enough, such that this constraint is met.
So what if Sn converges to s minus epsilon over 2 or something? Plus epsilon or
No, we want to give a little wiggle room underneath. I think if you put the plus, yeah, but the point is that you want a little wiggle room underneath, such that the sequence would be beyond that. But because like it's epsilon is arbitrarily small, that little wiggle room eventually vanishes, right? So yeah. A way to think about it is in terms, why don't we connect to capacity, right? That was a notion that we talked about previously. Let's call it, this plot will be rate versus number of channel use. Right? Remember, communication capacity was like roughly the largest number of bits per channel use that we could send. On this plot, I'm going to fix epsilon, be some number greater than 0. And then the kind of thing that happens is that for a sequence of protocols, you'll see this kind of behavior. Right? You're like converging to capacity. And this right here is the capacity, the largest number of bits that's sent per channel use. So this right here is the sequence. Right, and this is the limit, the limit in for the sequence. Right. This is the point is that you're always allowing a little wiggle room under. This is like S. This right here is S minus epsilon.
And this makes sense if you're approaching from below, right?
Yes.
If you're approaching from above, like your graph.
Yeah. If you're approaching from above, then we talk about a notion of strong converse capacity. And then lim sup is the relevant one. Yeah. So typically what we'll be doing is we'll be proving achievability theorems like we did with Shannon's theorem, where you're approaching the rate below. And then when we try to get upper bounds of capacity, we're approaching it from above. And then lim sup is the relevant one. Right. Yeah.
I still don't see how that's so lower
It's supposed to be a lower bound, right?
That's right. But the point is that this sequence is approaching this number. right? And I can always take a little bit less than this number, and then the rest of the sequence will be contained between S and S minus epsilon. Right? And so the lim inf of the sequence is indeed S. The lower bound is S minus epsilon, correct? Yeah. All right. Admittedly, I have also found it a confusing notion, but I tried to distill the way it presented it. And I found it was less confusing than Wikipedia. All right. But you know, in this example, the way I'm showing it, it's like the strong converse exists, and this is a situation in which you know lim inf is equal to lim sup. There's no difference between them. This is the situation where there's a distinction between them. But here, like you have the sequence. This right here is actually quite similar, right? Here you can think of this envelope here as like a sequence of lower bounds, right? And then the way I've depicted is that it's eventually convergent, right? So, like, if this were the actual lim inf, then I could, let's call this S, right? I could pick S minus epsilon right here, right? And then the sequence eventually, the sequence of lower bounds eventually gets within that window. Okay. Good. One thing you can show from the definitions is that lim inf is always less than lim sup. When you think of lim inf, you really should think of these words, greatest asymptotic lower bound. I think that captures it appropriately, right? And lim sup is the least asymptotic upper bound. And so then when you think in terms of those words, this inequality somehow becomes intuitively obvious, right? Yeah. Okay. So this is always true. And then if the reverse inequality holds, then you have equality of lim inf and lim sup. And then lim inf is equal to lim sup is equal to the limit, right? And you could use, like if the lim inf is equal to the lim sup, you could use the definitions to pick the n epsilon larger than the maximum of the both of them. And recover the definition of limit, which has the absolute value in both. All right. We're gonna move on to new stuff. Close out this part. Okay, I want to talk briefly about compact sets. This kind of thing actually isn't going to be so terribly relevant for us. It's more relevant when you're dealing with the infinite dimensional case, quantum states and quantum measurements for like bosonic systems. But here in the class, we're kind of exclusively going to be dealing with finite dimensional states, and everything will be compact. There will be no problem. Okay. So I just want to make that point. Regardless, let's say what this is. The subset S is compact if every sequence of elements has a subsequence that converges to an element in X. So it's like by taking a limit of a sequence of elements in the set, you can't get outside the set. You eventually stay in the set. And the key thing to remember for these is that for compact sets, the themum and the supremum always exist. We just call it infant soup. They're often abbreviated like that. Infant soup always exists, and they're contained in the set. Okay. And so the only thing I want to stress here is that for this case, if we're taking an themum over a compact set S, then you can always do this. And the function has to be continuous as well. Okay. You can always replace the themum with a minimum. So that means that there's always an element in the set that achieves the greatest lower bounds of the function of the set, of the value of the function of the set. So this is relevant for optimization problems such as semi-definite programs. And a similar statement can be made if you talk about supremum and maximum. And critically, the function f should be continuous. Set S compact. I believe this is the only instance in which the notion of compactness comes up in the book. That's what it's stated. All right. Another notion is convexity. We talked last time about convex functions and operator convex functions. We can also talk about convex sets. And this is critical for quantum mechanics because the fact that the set of quantum states is a convex set, the set of measurement operators is a convex set, simplifies the theory immensely and allows us to work with it in a reasonable way. It's also consistent with our notion of probability and doing independent experiments and collecting data. We'll return to that later. Convex set. So subset C is convex if for all elements in the set and the real coefficient chosen from the unit interval, think of it as like a probability, right? Then lambda u plus 1 minus lambda b is in the set. Okay. So if you've never thought about this before, it's useful to draw pictures. Like, you know, you can draw a picture and be like, okay, is this a convex set? Is this a convex set? Is this a convex set? And the way you think about it is take, you know, here we can just eyeball it and see that this is the circle or the square is a convex set. Take 2 points and draw the line between them. That's the lambda u plus 1 minus lambda b, right? This lambda is an interpolating parameter that connects these two via a line. And if every point on the line is in the set, then the set is convex, right? So you look at this, boom, convex, right? You can, whatever, right? And when this is convex, then, you know, obviously this one, Okay, and then, we'll see, like, if I take U and V could be quantum states. I can take convex combinations of them. That will correspond physically to probabilistic mixtures of states, which we can do experimentally. We can do the same thing with measurement operators. It's like flipping a coin and doing one thing or the other. All right. We also use terminology like convex combination. I probably have already used that without even realizing it. And we also have terminology convex hull of a system. Okay? Given a set, yeah, it could be a set of, it could be a finite set or an infinite set. This right here is a convex combination. And then critically, these px's form a probability distribution. Okay, so this definition right here is the simplest way to define a convex set, to take any 2 points. You can also define it in terms of arbitrary convex combinations. Right? You get probability distribution. Numbers between 0 and 1, such as they sum to 1. Yeah. So these give equivalent notions of convexity of a set. It's just simpler to. This is the simplest possible way that you can define a convex set in terms of 2. You get from this one to that one because 2 is a special case, and then you get from this one to this more general one by induction. And then take 2, then the set, combine it with another, keep going. All right. Convex hull. This is how you convexify an arbitrary set. Right? So convex hull is the convex set of all convex combinations of vectors in a set. So this, I think, again, is illustrated nicely with pictures. What is a convex hull? I could take this, right? The set consists of 4 points, right? And that's not a convex set because if you draw the line connecting A2, well, the set was defined only to have 4 points, right? The way you convexify this is imagine that these are like, you're looking down at the ground, you put pegs in, and you like put an elastic rubber band or something around it, right? As tight as possible. That's the convex hull in 2 dimensions. All right. Okay. Questions about that? All right. Yeah.
The convex hull is only relevant when that, like.
It's not convex. Like if it's already convex, the convex hull is the same. It doesn't do anything. Right?
So
Like,
what about?
if I were to take this circle, imagine like it's continuous pegs. If I put a rubber band around it, the set doesn't change.
What about the figure of
Oh, okay. It'd be like that.
Okay.
Yeah. It's like the tightest rubber band that you could put around this thing. And then that would convexify. Good question. All right. Next up is Minimax theorems. There's some other, we talked about von Neumann's quote about Shannon. There's another famous quote of von Neumann that he thought all of game theory was completely uninteresting until he discovered the Minimax theorem. So it's an important theorem. It allows you to exchange the order of optimization under certain conditions. In the context of a game, it's like one person plays first. They're trying to like minimize the value of some objective function. And then a competing player plays next and tries to maximize the reward function. You know, so maybe it's like a house versus a player in a casino. Or something, you know. All right, so Minimax theorem. In the class, we'll see min, max, max, min a lot. Many information quantities are written in such a way. And then we want to know whether we can exchange this order. Because often if you're trying to prove some upper bound or lower bound, it's helpful to know whether you can do that. Okay, anyway. So suppose this is the way, this is the situation we're facing, right? We have some function, and there's some, we're trying to minimize, maximize, or infimize, supremize. Those are words I don't know. And we want to know what is the value of this final function. You could define this to be like a g, right? Something to think about is that when you have this function, you optimize over y and you optimize over x. This thing no longer depends on x and y, on a particular x and y. It's like the optimal ones have been chosen. Now this is actually just some constant. Okay. So we always have just like we always had that lim sup is less than lim if is less than lim sup. We always have one version of inequality. So we always have this inequality always holds. I want to give you some intuition behind this expression. Okay, so before we talk about this inequality, think of this as a two-player game. And then when you look at this mathematical expression, it might not be clear who's going first and who's going second in the game. Okay. The way that what this translates to is that x goes first, and then y goes. Right? If you were programming this, you could think of this part right here without the infimization, right? And so it's like an x is chosen, and then you optimize, then you do the maximization. So this person, y, can react to the choice of x. And that's how it works in a game. Right? So x goes first, and then y goes. And once you have that idea in mind, this inequality is straightforward. If you believe that going second is an advantage, because you can react to the play of the first person. Like whatever play that person makes, you can then optimize based on the play. So that's what this inequality is expressing. You know, if X goes second, then that person can induce a greater loss for the Y person who's trying to maximize than if the order were flipped. Okay? So that's the basic intuition. And then in the book, we do a more like detailed proof, but that's essentially it. Another way to think about this is, I think it's in Calculus 3, you learn about saddle points, right? And you should visualize a Pringle chip. I think everyone knows what I'm talking about. Like whenever I travel to a foreign country, what is the first thing I go for? Pringles, because I know what it is and what it's going to taste like. Anyway, so it has, and then I think about the Minimax. So, you know, the Pringle chip, I don't know if I can draw it properly. I feel a little embarrassed now. So anyway, in one direction, it looks like this, right? But then in another direction, I guess, all right, there we go. There we go. Right. Okay. So this direction is the person who's trying to minimize. That if you have a minimax theorem holding, you have equality here. And you know, the person minimizing along this direction, it's always in their best interest to choose points that would lead to somewhere along here, along this minimum direction, right? Where the person that's maximizing is the variable this way. Right? And the point is that if the minimax theorem holds, it's like there's an equilibrium point, right? That's optimal for both players to play. There's an optimal strategy for both players to use, regardless of the order in which they play. Okay. And then the Pringle chip, this shape or the saddle, right, will help you remember the statement of the minimax theorem. Okay, when the order can be flipped. Okay. So the question then becomes, you know, this one always holds. When does the reverse inequality hold? And that's the statement of the Minimax theorem. I'm going to give you a simpler version of it than what's stated in the book. I believe the version I'm giving you is called the von Neumann Minimax theorem. So if these sets, S and S prime, from which the choices are being made, if those sets are compact, and if F is continuous, if F is convex in X for fixed Y, that's exactly this diagram here, right? Like, if we fix any of the variables along this direction, the function's convex. Right? And furthermore, if F is concave in Y, for fixed X, then you can fold. All right, at the bottom, then I'm just going to label this inequality as star. I'm going to say then star becomes an equality. Okay. There are different versions of the Minimax theorem. There's one from a person named Maurice Sion. think in the 50s. Sion proved it. And then there's one that we quote that two people in quantum information came up with. It's very, very relevant for optimizations involving Renyi entropy. So we'll use that one as well. All right. So 115. We're going to now move on to semi-definite program. Unless there are questions. All right. Those are a lot of different steps. And in semi-definite program, we'll revisit the minimax theorem. It's also relevant there. There's a way to think of an important concept in semi-definite programming in terms of the minimax theorem. So it's called semi-definite programming. This word programming might be kind of like an outdated or archaic word from the 60s and 70s that nowadays translates as optimization. At that point, computer, like now when we think of program, we think of a computer program. You're sitting in like code. Right? That wasn't as big in the 60s and 70s. And in the mathematical community, this was called program. So we can also call it a more modern term would be semi-definite optimization. And the goal is you're just trying to optimize some objective function over positive semi-definite operators satisfying the constraint. And indeed, I would say at this point, this is now a standard tool in quantum information. In the mid-2000s, it was a bit more of a mysterious thing, like a new concept for many people working in quantum information. But I would say now it's pretty standard and extremely important. Why? It's again this thing, quantum states, they're positive semi-definite operators. So if we're like optimizing some function over quantum states, then if your function is nice, then you're going to be doing semi-definite programs. Right? If you're optimizing over measurement operators, right? This is the kind of thing we're doing all the time in quantum information. Right? We're trying to send the most data over channel. We're trying to get the best precision from a measurement. Right? So often what the trick that people do is maybe the thing you're trying to optimize is nonlinear, then you can figure out some clever way of relaxing it to a semi-definite program. Then get a lower bound or an upper bound. And the thing we're trying to figure out what it is. Right? Capacity or precision of the measurement. All right. It's useful not only analytically, but also numerically. It's useful as a numerical and analytical tool. Why is it useful numerically? There are efficient algorithms that can calculate the optimal value of the semi-definite program. And in polynomial time, which is considered efficient from a computer science perspective. I forget the exact runtimes, but it's known in the literature. And in some cases, if you're clever, you can get analytical answers. So we've done that in our research group before, like using a combination of MATLAB and Mathematica, and like a week of slugging away, you can get analytical answers. Okay. So yeah, and there's a free package. Free packages for MATLAB and Python called CVX. CVX is for convex optimization. And for Python, of course, CVX Pi. Okay. So, you know, LSU finally, after years and years and years, got a MATLAB license. So you can use that. And you can use CVX, or you could use this is a free alternative, Python. They were both coded by the same research group at Stanford. There's a guy, Stephen Boyd, and his co-author, I forget the first name, but Vandenberg. They wrote a famous book about convex optimization. And along with that, they had students in their program, in their research program, write these packages. And most recently, they finished CVX Pi, and so people are using it. Okay, so there's different ways you can write some indefinite programs. We're going to write it in a way that's been promoted by someone named John Watchers, who's also written a book on information. So for this, we need the notion of a hermiticity preserving superoperator. I don't think I talked about this the last time. We did talk about superoperators, right? That's a linear transformation of an operator. So phi is a hermiticity preserving superoperator if the name gives it away, hermiticity preserving, if phi x is Hermitian when x is Hermitian, right? So it's a map that takes, it's a superoperator that takes Hermitian to Hermitian. Okay? All right, so now let's write the primal form of an SDP. But let's write what the input is first. Input to an SDP is phi, this map, right? So it could take linear operators on a d-dimensional Hilbert space to like d-prime dimensional. So phi, and then Hermitian A and B. Okay, so that's the input. And the primal SDP primal because it's the first one you consider. Trying to maximize this trace objective function over positive semi-definite operators. The constraint is that phi x is less than b. Okay. And then you're Tristan, right? So remind me what this operator quality means. Remember? Say it again?
No, sorry.
That's European data. Sorry to pick on you. At least remember we talked about this.
We talked about the city that's like how you subtract to matrices and everything. Yep.
So you want to state precisely what this means? Just essentially said it. You just have to tell me what precisely.
Yeah, so b minus 5x is b greater than or equal to.
Which means that b minus 5x is positive semi-definite.
Yes.
Good. All right. And indeed, you can check this condition by computing the eigenvalues. Checking that. Good. All right. So related to the primal SDP is a dual SDP. The dual SDP you get by flipping things around. You flip what's there in the objective function. I should define, this is called objective function. This is what you're trying to maximize. And then, this is called a constraint. This is also a constraint. Those are constraints. When you take calculus, you learn about Lagrange multipliers and constrained optimizations. This is going to be very similar to that, except now we're dealing with matrices and inequality constraints rather than equality constraints. But we will see a way to write down a Lagrangian with Lagrange multipliers to reason about this optimization. Okay, so let's make room over here. The dual SDP. How do you get the dual? It's going to be minimizing rather than maximizing. We're going to flip around what's in the objective and the constraint. Okay? So there's kind of a nice symmetry, and for me, it helps me to memorize it, to write it this way. So rather than x, optimizing over y, because we're going to think of the optimization variables as distinct. The objective function will have what's in the constraint. It'll have b times y. And then the dual constraint will involve the dual of phi. That's the adjoint of the superoperator. And then rather than less than, greater than a, and a is what was there in the objective for the primal. So you flip it around and you get this. Okay. Just to remind you, phi dagger is the adjoint of phi. And that satisfies if x and y are, yeah, you can make it better. It satisfies this. That was how we defined the adjoint of a superoperator. And then we said that if x and y were instead vectors and phi were a matrix, this is precisely how you define the adjoint of a matrix. It's like an abstract way of defining the adjoint of the matrix. Okay. I want to use a shorthand. We're going to call this SIAB. Use that shorthand for the primal value. And then for the dual, we'll use a similar shorthand, but with a hat. So there's a bit more terminology. I guess you probably feel like you're getting bombarded with terminology, such as like in graduate school. X is called primal feasible. It just means it's an X that satisfies the constraints. So it's like feasible for the task. I guess another word would be like admissible. I.e., X satisfies the constraints. It's like, if you present an X, it's at least something that can be considered for the optimization. If X doesn't satisfy the constraints, then you can't even consider it. Not even relevant. We have a similar terminology. Y is called dual feasible. If Y satisfies the constraints in the dual program. Y greater than 0 and Y. Okay. And it could happen for certain optimization problems that there's no primal feasible operator. Right? That can happen. So like I'll write an example of when you don't have primal feasible. Just keep this brief. So like suppose that phi x is it just maps x to 0, right? It just like trashes the input and maps it to 0. And then v is -1. Then this is not an interesting semi-definite program, right? Because like this constraint is just never satisfied. And so so the point is just to say that there exists semi-definite programs such that there's no primal feasible operator. And it's like, when you do in that case, then in this case, the convention is that the optimal value is equal to -infinity, like the worst possible value if you're trying to maximize something. That's the convention. All right. You could do similar constructions with the dual. Okay. So I want to give you a short proof of something quite powerful called weak duality. Weak duality. So this is the statement that the primal is always less than or equal to the dual. Just like with the max-min inequality, we always have one of them holding. It's very similar. Okay? We'll make an explicit connection soon. So weak duality is the statement that the primal is always less than or equal to the dual. This is very useful from an analytical perspective. Suppose for whatever reason, the primal is hard to analyze. Okay? But then when you write things in terms of the dual, it's easier to work with. Then, and your goal was to like upper bound some quantity you're trying to optimize. Then from weak duality, you can get an upper bound using the dual. So, and like in this class, we want to upper bound like capacity of a channel. We want to say that you cannot communicate at a rate larger than this. that's the use of that. So this always holds. Why is it true? The proof is very beautiful and just consists of like a few lines. So given x and y that are feasible. Okay. What does it mean? X satisfies this and this. Let's start with the value of the objective function for, let's make some choice. You know, we made a choice of an x that's feasible. So for that one, this is the value of the primal objective function. Question. So then, okay. I think I have to show you something before we do the next step. I have two matrices that are positive semi-definite. Then trace of C times D is a non-negative number. Okay. Why is that true? We're assuming these are Hermitian. We can do a short proof of this first, because like I think there's a risk I could show the proof and be like, huh? Right? So I think we should do this first. So if C is Hermitian, you can do a spectral decomposition. Right? All these eigenvalues are non-negative. Same for let me write these ones as 5. These eigenvalues are non-negative. These eigenvalues are non-negative. Right? To evaluate trace of CD, and what you'll find when you do the calculation is that it evaluates to, it's going to be a double sum of CI, DJ, and then absolute overlap squared with those. So the point is, this is non-negative, this is non-negative, this is non-negative. You're summing non-negative, so then, all right? It's the basic thing that we need to understand this. All right. So then, from this, we can infer like I have K, it's positive semi-definite, and L greater than M in the operator order. And from this one, include the trace of K times L greater than trace of K. Right. So why is that true? Well, Tristan reminded us that L greater than M is the same as L minus M being positive semi-definite. Right? And then this inequality we can write as trace of K times L minus M. And then, it's a special case of this one. All right. All right, so that we're going to use. That's a basic thing that we need for this weak duality. So we want to connect the objective function of the primal to the objective function of the dual. Right? And we want to try to show that this trace AX is less than trace BY. Well, we made the assumption that X and Y are feasible. So that means they satisfy this constraint and this constraint. These constraints. So they can use this constraint and this kind of inequality, this trace inequality, to say that this is less than trace Y dagger Y. Hey, No, X, sorry. Right? That's fine, right? And then now, use the adjoint property. Take phi dagger and flip it around to phi acting on X. Right? Now we have phi X. If X satisfies this constraint. Boom, we apply that one. Increase Py. That's essentially the end of the proof. Why is that? We've shown that this inequality holds for all feasible X naught. Right? That means if it holds for all, it's extremely strong. And even though it's said to be weak, it's quite strong. So this inequality holds for all feasible X, for all feasible Y. That means I can like take the optimal or n optimal X. So that means I can maximize the left-hand side, I can minimize the right-hand side. But it's still true. It's holding for all of them. That's the end of it. And maximize left-hand side and minimize right-hand side. And that's the end. That's the end of the proof. All right. Got about 7 minutes. I think in the remaining time, we'll make. I don't know if we can do it. I wanted to make the connection with the max min inequality. We could either leave now or spend like 5 minutes beyond the class. Who? All right, that's not fair. Who would like to stay and listen to it, or just leave it for next time? I guess the issue is that there's going to be a weekend, so you might show up on Monday. Like, what on earth did we talk about last time? Who would like to stay and hear the proof? Green out now. All right, so we'll try to be short. I guess I first should ask if there's questions about this. Connection between connecting weak duality and the max min inequality. So just to remind you, the max min inequality is this thing that we wrote through this sup y if x fxy less than or equal to mx sup. So to connect them, we're going to write down a Lagrangian corresponding to this optimization problem. Okay? So we're going to think of the dual variable y as a Lagrange multiplier. Okay? So we'll take the objective function and take this operator inequality, multiply it with a y, and then take the trace. And then that will be like a Lagrange multiplier. So I'm going to write it big L, and then this is a shorthand for it's a function of 5 things. I, A, B, X, Y. Okay? All the different things that are involved in the optimization problem. So the objective function, trace AX. Then plus trace BY. I'm going to first write it like this. I'm going to take B minus phi X, right? Take this constraint, and then multiply that by a Lagrange multiplier, Y, which is positive semi-definite. Because this is an inequality constraint, we take the Y to be positive semi-definite. Right. And then another way of writing it, if we just do this algebra, trace AX plus trace BY minus trace YX1. That's the way of writing. There's, okay, so those are 2 ways of writing it. The third way is to use the adjoint and think of X as a Lagrange multiplier for this constraint. Okay? That's the duality relation. So you can take phi X and make it phi dagger on a Y. Right? And then we can rewrite this as trace BY plus trace A minus phi dagger Y. So when you look at this formulation, you think, oh, okay, this corresponds to taking the dual objective, this inequality constraint, multiplying it by positive semi-definite X, which is like a Lagrange multiplier. Okay. So how does this relate to the max-min inequality? Well, let's do this kind of thing with this Lagrange function and see what we get. Okay? Let's do a min and a max. Let's first do this one. So space. Let's first do supremum over positive semi-definite X and femum over positive semi-definite Y of the Lagrange. Well, let's just substitute in. And we want this one, this first one. Trace X. Okay. So in this expression, we can ignore the sup over X for a minute. And then the objective function, the first term doesn't depend on Y. Right? So we can bring it over. Just this one. Let's do that. And now let's think about this one and how it corresponds. What is the connection of this function to this constraint? Okay. So let's suppose that the constraint is violated. Suppose the constraint is violated. Then what happens? Suppose constraint Ix less than B is violated. And notationally, people will write this as phi x not less than. And this notation is important because remember the order is a partial order. So it's not like if this is violated, you have the phi x is less than b, right? You have that for real numbers, but for matrices, if this is violated, it just means that, well, b minus phi x is not positive semi-definite. That's what it means. So then people adopt this notation to denote that. Okay. So indeed, if it's violated, this means that b minus phi x is not positive semi-definite. So then we roll through the definition of what does positive semi-definite mean. Well, if it's not positive semi-definite, then that means there exists a vector such that this number you get is strictly less than 0, right? That's what it means in the constraints model. So then the idea is going to be to construct the y from this side. Okay? So let's pick y equal to c, which will be a positive scalar, times the outer product of psi with itself. That's a legit, okay, and then just clarify c greater than 0. So this is a positive semi-definite operator, right? So it meets this constraint in the y. So then if I take trace of b minus phi x y, and we rewrite it, well, you'll get, for this choice, you'll get that it's c, and then exactly this expression. B minus phi x sandwiched by psi. So what does this mean? Stepping back a bit. If the constraint's violated, we can pick y to be this positive semi-definite operator. And then this is an infimum over all positive semi-definite operators. So we can actually take the limit as c goes to infinity, like a sequence of y's, right? And what will be the value of this? It'll be minus infinity. Right? So the argument here was, well, taking the limit as c goes to infinity, this expression here is equal to minus infinity. Okay? So the point is that if the constraint's violated, you can pick a y to do the worst possible thing to the goal of this person who's trying to maximize the objective function, right? So like there's a one-to-one correspondence between this optimization function and the constraints. How do we summarize it? Let me erase this. So this function, let's just write down what we found. But it equals minus infinity if y(x) is not less than. Right? That's what we argue. Okay? On the other hand, if the constraint's violated, v minus phi x, sorry, if the constraint is not violated, if it's satisfied, v minus phi x is a positive semi-definite operator. Y is as well, right? And so by these arguments that we gave here, in that case, this number is always greater than or equal to 0. And so you should just pick y to be the 0 operator to minimize this effect. Right? So then that actually proves that this expression is equal to this one. Right? Because like if the constraint's satisfied, then this part adds nothing to the objective function. It adds nothing and it takes nothing away. However, if the constraint's violated, it's like, excuse me, you completely screw the objective of this person who's trying to maximize this function, right? Because like if the constraint's violated, this person can pick a y such that the objective function is simply minus infinity. And so when you think of it in terms of a two-player game, this person had better pick an x that satisfies the constraints, or that person is guaranteed an infinite loss, right? If it's gone to hell or something. All right. So okay. All right. So this whole argument shows that this is equal to S phi A. We're essentially done. The only other point I want to make is that if we switch the order of optimizations, you can play the whole logic game that we just played about this, but to argue that you'll get the dual. Okay? You can play that whole game. So let me write that down for the same reason. F over y 2 of x Lagrange is equal to dual. Okay. So now we've made the connection, right? Like replace f with the Lagrangian, and we know that this max-min inequality always holds. That means that this one is always less than or equal to this one. Right. This optimization with this order is always less than or equal to this optimization by max-min. That's the same statement as weak duality. Okay. So that's it. Actually, we went 10 minutes over. So, let's leave it at that unless there are questions. Yeah.
It's a primal problem.
Yeah.
Okay. Dual is 5 years, right?
Like that.
Yeah.
Yeah.
If you take the dual of same dual problem and you do the reverse process,
You go back to the problem. That's right. Yeah. They're duals of each other.
they lose each
Yeah. It's not like you get something different. Yeah. It's due to the linear structure of the objective function. Right. And you're optimizing over the positive semi-definite column. Yeah.
This might not be like important, but it's just like something that whenever we do Lagrangians, we can probably formulate some variation, calculus variations. Is there like an analogy of sort of matrices and supermatrices? Is that like something that we can do?
I mean, there is a matrix calculus of derivatives. And so, yes, you can do this.
I'm sure it's not like 4 hours.
It's a good point to connect to previous knowledge. Sure. Yeah. I don't think we'll be doing such things in this class, but it is important. to know. Yeah, the thing is, like these STPs, they're linear, and so like all these, if you wanted to take derivatives, they'd be very simple. So you can just use this kind of reasoning. If you were dealing with more general convex optimization problems, where the objective function is convex and like the constraints are nonlinear but convex, this would be useful. All right, so remember, homework's due Wednesday. If you have questions, you're welcome to email me or come to office.